Hi everyone, welcome to the IoT track. Would you give a warm welcome to Aiden, presenting workplace environment sensing with Python.
Cool. All right, thanks. Hi everyone, I'm Aiden. My background is in electrical engineering, and I work at BVN Architecture just up at Pitt Street, up the hill. And today we're talking about workplace environment sensing. It's kind of my adventure into embedded Python and really CircuitPython in the context of a project and just how that went, my experiences, and how I feel about using it for a project. Yeah, awesome. So I'm going to show you 3 pictures, and I want you to guess what's missing from them, from these buildings. 3 buildings. So here's the first one, and the second one. And the third. Anyone can guess? People. Someone said it down the front. There's no people in these photos. And it's really odd because people seem to be really underrepresented in buildings. You can get this award, one of the most significant awards in architecture in New South Wales, and the building hasn't even been occupied. That seems a little bit off to me. What is a good building, however, are these things. You have some good photos. We saw them just there. It fits with our self-image as an architects. We get awards given by other architects to fit the same self-image. We get repeat business. It's a pretty good pat on the back. Not getting sued. It's a pretty big one. Although, having said that, you can still get sued and get repeat business. It's not a game changer. And profit. You make money, you're doing pretty well, right? Again, what's missing? A kind of lack of focus on people. It's just a little bit off. So this is an image of a siege gun in World War I. I think this particular gun is called the Paris gun, and it shot 67 miles, 100 and something kilometers, into Paris from quite far away, and because it was so far away, the curvature of the Earth meant they couldn't see where they were shooting. They didn't know if they hit the target or not. I mean, it's quite a big target. So what they would do is they would get someone riding on horse for a day and there and a day back and go, yep, you got it, or no, you didn't. And it's this slow back and forth. And they might have fired, 10 other times and completely missed the whole time. And this is kind of the analogy I feel at the moment for architecture, where kind of you can start your career as an architect, and your first building, you can be well into your career before your first building's even made. So this is what we want to be like. We want to be a guided missile, the kind of perfect control system, constantly changing its direction, going right to the target. So yeah, architecture is about making big moves with very little feedback. We want to change that. So this is a missile guidance missile system, I think from the 1960s. So that's the question. Like, what is our missile guidance system as architects? When you come to the web is like completely instrumented. It's got, you expect it to be, what's going on, who's coming, what's the traffic, what's happening. That's completely normal. No one seems like that's off. But when it comes to the physical world, it's kind of odd to instrument this area, especially the workplace. You put sensors and everything there. No one's happy with that. So, we're kind of still with the horseback spotters running to Paris and back. Yeah. So this is kind of the picture I'm seeing. We want to be. This is Amazon Go in Seattle. I'm sure people have heard of Amazon Go before. They have sensors everywhere. They've got cameras everywhere. And what happens is you walk into the store with your app, you get an RFID, you tap, you grab the stuff you want, you put it in your bag, and you walk out. and they know exactly what you grabbed. Decked out, love it. This is like kind of the dream case for a data scientist, like a data scientist's wet dream for an office. You got everything there, you know exactly what people are doing, you get this kind of perfect feedback loop of awesome data, and then we can go, okay, this is what we're doing wrong in our design, this is what we can do. But we don't have infinite money, and privacy concerns are definitely there if you've got cameras everywhere in your workplace. It's a bit more like home. So it's kind of this, like, you know, this curve. You've got the dream up here on the far. That would be the Amazon Go in the workplace. And then you get this kind of minimal case where you have this little tiny embedded sensor just measuring maybe temperature and light. And it's super cheap, super easy. Have a couple in there. So we've kind of hit a middle ground with our sensors. At first, it was this guy. We designed this. We were designing for round 2. We got them made. And then we did our due diligence, and we found a sensor with all already made, with everything we wanted, but it had more, and it was cheaper. Oh, well, it happens, right? And this is it. This is the Circuit Playground Express. I think someone was using it in the first talk in here this morning or later. It's got all the sensors we want. What it does is it sits at your desk up there, plugs into the thin client computer there, and networks away and collects the data. I'll show you guys. I've got it here. So this is it. It's got a temperature sensor, a light sensor, sound, which is what the other guy had, but then an accelerometer, infrared, a speaker, which is kind of more 8-bit than anything, and more memory. And the more memory enables us to use embedded Python, which is a lot easier than programming in C++, well, at least to me. I think you can agree. But I did start in C. I did try it. I thought I'd give you a case for embedded Python in case you're not there, but I think I'm probably preaching to the choir. So, you know, C and C++ are definitely significantly faster at runtime than embedded Python, and more compact. They don't need as much space and memory. You've got a lot more control. It's not always a good thing, though. Some people are saying that C++ is becoming more Pythonic anyway. I don't know about that. And the biggest downside is probably that it's hard to learn. Whereas embedded Python, it's nice and easy. We love Python. Quick development speed. So much faster to learn. For me, in my organization, there's not a lot of C and C++ programmers. There's a lot of Python programmers. So I've got a lot more support. Having said that, you need a lot more memory. It's not quite real-time response, which sometimes you need. But for me, the two big ones that pushed me over the edge to use embedded Python were the comparison of these two things. And I said development speed is much more important in this case. Let's get it out there, collect some data, and we can come back and fix the hardware. Yeah. Also, I mean this was this year. Python was the top language by IEEE Spectrum for embedded programming. And it was also the top language overall. And one of the reasons they said was because it was considered an embedded language. So, you know, it's doing quite well. Yeah, there's the top 5. So the kind of embedded Python languages you have are MicroPython here, CircuitPython. They're both open source. CircuitPython is just a fork of Adafruit's fork of MicroPython. It's a bit younger. It's about 2 years younger, and it's more beginner focused, so it's has less features. Ooh. Then there's a non-open source Xerenth. Sorry. You have to pay per unit, so I'm probably going to stay away from that. It's more kind of. I'm sure someone will enjoy it, but not my cup of tea. And then, I mean, for IoT, really, you can just get a single board computer and normal C Python works quite well. BeagleBoard, Raspberry Pi, they work fine. So they're the kind of options, but I picked hardware first, and Adafruit's got a lot of support, so I went straight for CircuitPython to get up and going. So I'll give you a rundown of how it works if anyone is interested. So it's so nice and easy. If you're programming in C, you have to compile it across, target the right firmware. When you plug into CircuitPython, or I think MicroPython as well, it comes up as a nice drive. You just drag and drop, you hit the code across, and there it goes. It's beautiful. You've got code. It has to be called code, and then you've got a boot, and then you can have whatever Python and library stuff you want there. It's really easy to use. It's really, really intuitive. Just import. It's really, syntax is almost the same as Python. Just import. You can import here. There's subsets of Python standards, and then there's CircuitPython specific, and then you can just import your own thing, obviously. Very nice. Communications, if you want to print to the serial port, grab your data, you just call the sensor. With CircuitPython at the moment, they haven't implemented non-blocking serial input, and I'll explain my way of getting around that, but I essentially just used a file buffer and a bit of polling. Cool. All right, well, we're going for time. Yeah. So why don't we do a code walkthrough? I'm going to show you a little demo. Ooh. How's that? Good. And got a little. I've got a little webcam here and my CircuitPython, and it's kind of more or less a light meter. I put my shadow over it, and it goes down, and then if I get my phone light, it should go up, right? Pretty basic stuff. So, how does that work? So, easy imports of libraries. You got sys, os, time, and math. Some CircuitPython specific stuff, accessing the pins, accessing analog devices, and this is the RGB LEDs. And then I've got my own function outside in my folder, just some mapping stuff for converting the light data to the 10 neopixels on the board. Oh, away from it. There's 10 here. Yeah. So yeah, we just define normal stuff. We get some just some basic variables, and then here to get the access to the light sensor, I call this basic. This is the pin where the sensor is, and I make it an analog device. Got my object, nice and simple. And to call it, all I need to do is say light.value. Nice and simple, nice and easy. Cool, and then I've got this defined over here. It just constrains the values and converts it to a logarithmic scale using a math library. Yeah. And then we empty the pixels, and here we loop over each pixel, and we change the colors. So here, based off the pixel value, this just handles coloring and scaling, and we take the minimum and maximum. And that's the simple event loop we have. So, yep, call the main. Well, yeah, and then let's get back to, let's show what I'm actually doing with BVN. This is just a kind of dummy demo, so we can understand the code quite simply. Let's get it. Yeah. So this is what we're doing up at BVN in our office. We have some sensors, 5 sensors placed around the office, and we can see the temperature values, sound, and light. So each one is grabbing it just like very simply with CircuitPython. It's plugged into a Raspberry Pi, and we're pushing it to an AWS server. And then we're coming up with kind of comfort level that people can see. We're going to add more sensors to that. We're going to get into it, but I'll show you how that works. It's quite similar. Here we go. So let's plug that guy in. Okay. Ooh. So again, just import our libraries like normal. Here, I'm using this for testing purposes. Just checking which implementation it is. If it's CircuitPython, then run it like in main down here. Ooh. Otherwise, we can test each function. Now, with CircuitPython, it needs to be called code. There we go. Right? It needs to be called code.py. Now, if I import code for testing purposes, there's already a library called code, and I get a bunch of issues. And also for getting good with Git, keeping it into my repo, because I don't want to keep it on the board at all times. I've set it up with VS Code, so when I save it, let's get over again, it just copies it across to the board. So if I make a change, oh, I haven't got it up. Simple CP whenever I save. Copies it as code to the spot I want. Really nice. If you're not into VS Code, there is Adafruit recommends Mu, which has the REPL involved. It's quite nice to use. They even have a way to graph your code, but I much prefer VS Code, so I'm going to stay in VS Code. Yeah, so we'll go into the tricky part. So nice imports. We'll come back to this. The pixels and air pixels, because I'm going to be changing some colors. The thermistor is just the temperature sensor, light, the microphone. Some maths I need to do that aren't in the maths library. And then serial is just a wrapper for print. But having print everywhere is not as good for the eye. A bit harder to understand. So because we don't have access to async, we don't have access to, well, we have a single chip, so I can't do any threading. I've just done a basic event loop. And basically, I don't even want to call it a scheduler. It just times how long has it been since I want to do the sample rate, and calls it when it's ready. So we'll go to the main loop. So we call time monotonic. We get the time. We'll grab the light value. We pass it through. Is it time to call it yet? And it can handle pretty fast stuff. You know, less than 100 milliseconds. It's quite simple. So getting the data is the simplest part, really easy. It was super quick to get up and running. The tricky part, because I don't have non-blocking serial input, was handling that. And what I've done is I've done a file buffer. So what I do is I just poll the size of the file. So we've got a file called buffer.txt. And from the computer side, if I put in an RGB value in hex, it'll read it and change the color. And then, unfortunately, the CPU can only be read or write. And because we want to read from it, we have to make sure that the host computer also deletes what it's done. So I can't do a destructive read. But so here we just grab, don't recommend. Let's open buffer.txt. Simple. And get my camera, which isn't showing. So if I just change the values in there. Yeah. It's nice and, oof. That's the brightest it can go. So yeah, now we have access. We can, and what this allows is we've limited it to 3 colors: red, orange, and green. And that's kind of like, you have some use case for this thing. It's not just collecting your data, you can use it. And what it does is it says, if it's green, you can come talk to me, because we're in a big open office space. If it's green, come talk to me. I'm free, come chat, I'm not busy. Orange is like, I'm doing work. I'd prefer if you didn't come and chat, but I don't have a hard deadline. And red is, just go away. I'm busy, F off. And so everyone has that access. We've got a little Electron app we've written up. I'm not going to show that because probably don't have enough time. So we have some use for them, but because we can change the color, I'm going to eventually write a domain-specific language for this. We can have party mode. We'll have a big red button up at the reception. You press the big red button. It's Friday night. Everyone, let's go have some drinks. So, there's room for extra features. Let's delete that. How am I doing for time? Yeah. So what else should we show? Well, is there anything? I guess that's probably need for now. We can have a long question time. You can ask me about the code. Yeah.
So any questions? Yeah. Oh, well.
Can you talk a little bit more about the testing method you used? We could see those sort of, if we're in CircuitPython,
yeah,
do blah, but I didn't completely understand how you actually affected your testing using that.
Yeah, so when I run normal CPython, I can't, see I'm getting the errors here, I can't import these values, and I can't run a lot of the code that I want to do. So I just have a test script. It just tests each function separately, and I import code dev, and checks what implementation it is. Is that? Yeah.
Howdy. So you mentioned that you've used this in your office to gather the data of the office temperature, light, and what was the other one?
Sound levels.
Sound levels.
Yeah.
Have you been able to use that data to improve the office at all? Any changes you've made with that data?
We haven't made any changes yet. We're still in quite at the early stages, but yeah, we're trying to understand it because there's a lot of research around this kind of thing. It's mostly reported people how they feel, or an engineer comes in with a high-vis jacket and they get a big giant sensor and they stand in the middle and they go, yep, it's that sound level, and by standing there, they're actually affecting what's going on. So we're in the research stage trying to understand how it affects, how it moves spatially, especially in open office space.
Thank you.
Yeah.
G'day. You measured a bunch of discrete points, like where your sensors were. You've got the temperature at that point, but that map shows a continuous change in temperature or comfort or whatever that one is. How have you done that?
It's just basic interpolation between the points, so it is kind of cheating. But you can imagine we're assuming it's a linear interpolation across the things. Yeah, it looks cool, right? Yeah. But yeah, we do plan on getting a lot more sensors in there, and that'll be more realistic. Yeah. Well, get the mic.
It's okay. Hi. Great talk.
Thanks.
What's the kind of distribution of what's the range, I guess, of these sensors? Are you aiming for more of them, or like what's the dimensions of how far you space that?
Well, at the moment we're going for 100 in this space, which is pretty significant. I think for temperature it's not paramount how close, because it's quite noisy anyway, and I think and with lighting levels it's quite difficult because it's very directional, orthogonal to the light position. But especially with sound, the more we have, the better it is. That seems to be one of the major complaints with people, especially in open office spaces, co-working spaces. So, yeah, as many as possible is really our aim. But it's kind of limited to either the computers we're plugging into. So, we only have 170 people in our office, so that's probably our maximum, or the number of single board computers we can connect to a single point, the Wi-Fi or Ethernet. Yeah. Who have you got?
Hi, thanks for your talk. It's really cool. I was just wondering, what's your calculation that you're using for the overall comfort map, and whether you've considered getting the people that have the sensors to self-report comfort levels at all?
This comfort level is just completely arbitrary right now. But what we're doing with our app is we have a little pop-up that is asking people how they actually feel, so we can match the two next to each other. It's actually quite a difficult thing to do. How do you ask the question? How frequently do you ask it? Do you ask them like 3 times a day? How many times is too much? What's statistically significant? So we're trying to get the maths on that to ask the people the right questions. But the implementation's there, and we want to really match up the two: temperature, light, sound. How are they actually feeling? Yeah, because these things, especially temperature as well, it matters what. There's a lot of factors involved, like what people are wearing, temperature outside, the temperature of the wall. Yeah.
Just curious, because we do some stuff in similar areas, but did you have any resistance to installing microphones on everyone's desks?
Yeah, absolutely. And not unreasonably, Hence why I was pointing out the middle ground, We're not going to... Computer vision, again, would be awesome in this space, but that's an even harder sell to people, having cameras everywhere. And no matter what you say, no, we promise we won't look at it. No, we promise we won't do it. It's all through a computer. People aren't going to believe you. But we're pushing through. We're showing them the code. We're showing them as much as possible. And it is going ahead. People seem okay with it now. I wouldn't say happy, though. Yeah.
What are you using for your visualization?
So I didn't do this visualization, so I can't go into probably too much detail. But this is an Electron app, just some nice JavaScript node stuff. Ben is in the audience here. He probably answered the question better, but Plotly. Yeah.
Probably got time for maybe another question. Yeah.
You said that the sensors are attached to each person's computer. Do these people have laptops? And if they walk around, how do you then change the location of the sensors?
We mostly have thin clients, so essentially a desktop. And we just installed desks a few months ago that can move anywhere we want. They're on wheels. We've got this boom that comes down, and we can power and gain internet wherever we want. So that's actually, that's not a problem at all. Yeah, they all stay with the desk. And unfortunately, people with laptops, there is a handful of people who prefer a laptop. They don't get measured. Maybe they're happy about that, I'm not sure.
Probably just another quick one if anyone has one more question. That's it. Cool. All right, cool. Give it up for Aiden.
Thanks.